All right, welcome back to Calc 1. We are going to start Chapter 2 today. Chapter 2 is all about derivatives. We're going to shift gears a little bit. We've been talking about limits in the previous chapter. Now, let me be honest with you. You're never going to be done with limits as long as you're in calculus. Limits are the foundation of calculus. And if you take, Calc 2, Calc 3, more advanced calc classes, you're always going to be talking about limits. So we can't forget limits, but we are going to shift a little bit. In fact, um, limits are the foundation for derivatives, and we're basically, for this video, going to do more limits. But yeah, we'll take a look. Let's see what happens. Derivatives. What's a derivative? One word for you: slope. Derivative is slope. Now, yeah, depending on the context, there may be a little more nuance than that. And when you use the word derivative, you could say, let's find a derivative, and that could mean, I guess, one of two basic things. Find a specific derivative, like a specific slope, or it could mean find what we call a derivative function, a function that gives slope at all points, possible points. Different meanings, different context. Kind of like, bat. Bat could mean a baseball bat, or it could mean the mammal that flies around. Okay, so different. What's the word for that? Homonym, maybe? Is that right? I don't know. We'll see. So you can correct me if that's the wrong word. But different meanings depending on the context, but otherwise the same word. So derivative, you can use it in different contexts, but in general, slope, some sort of slope. Now, you talked a lot about slope in your previous pre-calc classes. You know, algebra, pre-calc, you talked about how to find equations of lines. Maybe lines that were parallel to each other, or lines that were perpendicular, or lines in point slope form, or slope intercept. You spent a lot of time talking about lines in your pre-calculus courses. So lines and their slope. But here's the thing: with a line, you have a constant slope, or suppose you could have an undefined slope if you have a vertical line. But if it's a non-vertical line, you have a constant slope. The slope is the same everywhere. But if you have a curve, all kinds of different curves, ones you're familiar with, like parabolas, or the square root function, or the cubic function. All of these curves, they have different slopes at different points. And so we say that they don't have a constant slope. So the key question is, how do you find the slope? Well, it turns out that you can find the slope by finding what's called a tangent line. A tangent line, I guess for a working definition, we could say it's a line that touches a curve at exactly one point. Now, one point, as long as you restrict the domain, perhaps, to be very small, because it is possible that if you look look way over here or way over there, that the tangent line may cross the curve again. But a tangent line here. Let's just let's sketch them real fast. Let's see if we can get some shapes here. Here we go. Something like a parabola. Now I'm not. Actually, let's just forget it. No parabola. How's that? Actually nice. Okay. So we have this curve. If you want a tangent line, say like right over here, the tangent line is going to be a line that just barely touches the curve at that point. Barely touches. I like that. That's what a tangent line is. Okay. And if you can kind of imagine, what these might look like at different points, over here, the tangent line would look about, if I could draw a straight line, would look about like that. Now, clearly, this tangent line, if I extend it, is going to cross over here again. But as long as I'm just focusing on this little area over here, it's only going to touch the curve one time. And if I look over here, you're going to have a tangent line, that looks like this. Okay? So those are tangent lines. And here's the deal. If you can find the slope of the tangent line, then you can find the slope of the curve, because they're the same thing. So the slope of the curve at this point is the slope of that tangent line. Same thing over here. The slope of the curve at this point is the slope of that tangent line, and same thing over here. So This is called the tangent line prob. It's this super old prob in mathematics, and it was one of the catalysts for inventing calculus. This is a motivation for inventing calculus, that we wanted to find the slope of a tangent line, and calculus was a set of tools developed to do so. So how does this work? All right, let's take a look. Let's revisit the slope equation from college algebra. Here you go, right here. That is just the plain old slope of the line that passes through 2 points. So if you don't know that, I won't say shame on you, but shame on you. You should know that. Okay, that's that's been in math class since a long time. If you've had college algebra and intermediate algebra, all that stuff, slope formula is a big deal in there. So there's the slope formula. Okay, now we're gonna write it just a little bit fancy. That's all, just a little bit fancy. Okay, imagine we have this picture over here. So let me focus over here. So I want to find the tangent line, the slope, but specifically the slope of the tangent line at this point C. Anytime you see C, the letter C in this class, chances are it probably means a specific x value. So here the specific x value is C, and that's where we want to find the slope. We want to, C is going to be the value of x where we're interested for some reason or another. Why? I have no idea. That's what textbooks do. So that's what I did. All right, so C, we have this value. We want to find the slope right there, okay? We're going to use what's called a secant line. Now, a secant line, it's not a tangent line. A tangent line, we said crosses a curve at exactly 1 point as long as you're really close to C. But a secant line, and don't think trig here. A secant line is simply a line. I think the Greek word, it comes from like cut. It means to cross a curve in 2 places. So here is a secant line, this dotted line here. Okay, so we have a sorry, that's not dot, that's dashed. We have a dashed line here, and that's the secant line. Now, what 2 points does it pass through? Okay, it passes through C, comma f of C. So this is a curve. I guess I never labeled the curve over here. We have f of x. That's a curve, okay? And then we have C, f of C is this point right here. So it's the x value, C, and then the y value you get when you plug in f, just f of C. We don't have a specific function, so we don't have a specific number to put there, okay? Now, what about this value over here? I have it labeled as C plus delta x. Now, don't let delta x throw you for a loop. Delta x simply means a small distance on the x-axis. So, you see here I have it labeled like this. It's the small distance on the x-axis. Likewise, delta y is a small distance on the y-axis. Don't let those throw you off. That's all they are. Delta is a Greek letter, and in fact, this is a capital delta, a little triangle symbol. Capital delta just means change when you see it in math class. And so delta x means, actually, I should back up. Delta means a small change when you're in math class. And so delta x means a small change in your x values. So this point over here is C plus delta x, the x value is. So if you want to label this point, then we can label it as the x value, which is C plus delta x, comma, well, what do you get when you plug in? If you plug into your function, you get f of C plus delta x. So f C plus delta x. So you have 2 points. What might you be able to do with 2 points? Well, you can find the slope of the line that passes through 2 points, just like you did in college algebra or intermediate algebra or pre-calc. So we have 2 points. If you want, you can label them, I suppose. Here, let's see, let's get a different color here. To make the arithmetic work out a little easier, let's call this one x2 and y2. Let's call this one x1 and y1. Okay, so we have 2 points. plug into your slope form over here. So y2 is f of c plus delta x minus y1 f of c over x2, which is c plus delta x, minus x1, which is c. Okay, so we plug in, substitute known values, and then we can just simplify the denominator just a little bit. So the top doesn't really simplify at all right now, but the bottom we have c plus delta x minus c, so you have the c's add to 0, and so you just get delta x. So the slope of this line, the secant line, is right here. M equals this. Okay? Now, we're going to use that in just a moment to find the slope of a tangent line. Here's the idea. What if I took the limit as delta x approaches 0? What does that do graphically? What that does graphically is it pulls this point c plus delta x comma f of c plus delta x. It pulls that point closer and closer and closer and closer to c. That is because this distance is getting smaller, and so it pulls that point closer and closer. And if we take the limit as delta x goes to 0, it turns out we get what we call the tangent line. That is our solution to the tangent line problem. Now, let's go through a small example. Let's see here. All right, consider just a quadratic function, f of x equals x squared plus 1, and the point 1 comma 2. Determine the slope of the secant lines, so no tangent line right now, just secant lines, that pass through P and Q, which is 1 plus delta x, comma f of 1 plus delta x, for these different values of delta x. So we're using the slope formula from the previous page. Okay, now I'll jot it down in case you, well, you have it on your notes, but I'll jot it down here so we can all see it. So the slope formula from the previous page was m equals f of c plus delta x minus f of c over delta x. Okay. Now we have a specific function and we have a specific point. So there's our point that we're interested in, and there is our function. So we can actually plug into this slope formula and get a specific version that works for this function and this point. Okay, so let's see what happens. Let's plug in to find our specific slope formula. First of all, we can plug in 1. 1 is your x value, your value of c. The value of c is the specific x value you're concerned with. So here, c is 1. So again, that tells us c equals 1. Okay, so we can plug in and we get what? F of 1 plus delta x minus f of 1 over delta x. Okay, but what does it mean to have f of 1 plus delta x or f of 1? Again, this is going back to algebra class. That means evaluate the function at 1 plus delta x, or evaluate the function at 1. In fact, we need to do both. So let's evaluate both of those functions. Let's do f of 1 plus delta x. This means take 1 plus delta x and plug it into x squared plus 1. So we replace the x with 1 plus delta x, and we square it, and we add 1. So that is f of x plus delta x. But then we need to subtract off f of 1. So we plug in 1 into x squared plus 1, and we get 1 squared plus 1 over delta x. Okay. And then we could simplify this a little bit. I'm not gonna. I guess we could do a lot of simplification. I'm not gonna simplify it all the way. I'm going to just simplify this basic arithmetic up here and say this gives us, let's see, 1 plus delta x squared. Okay, we have 1 squared plus 1 is 2, so 1 minus 2 is negative 1 over delta x. Now, you might tell me, well, yeah, you could simplify this a little more, and you'd certainly be right. I'm going to leave it like that for the time being, though, because that's enough for the exercise we're working on. This is enough simplification. Okay. In fact, in the next exercise, we'll get a little more. We'll see how you can actually simplify this further, but we'll do that in a second. So here is our specific version of slope here that we can now evaluate at different values of delta x to find the slope of 3 different secant lines. Okay, so here it says, okay, let delta x be 0.1, 0.01, and 0.001. So basically, we have 3 situations. We have the secant line through P, which is the same, is not changing. So P is 1, 2, and Q is, let's see, 1 plus delta x. So actually, let me back up here. Let's erase that. Let's just say let delta x equal 0.1. Okay, that gives us the slope of the line through 1, 2, and 1.1, f of 1.1. If you plug in 0.1 for delta x, you get 1 plus 0.1, 1.1, f of 1.1. Okay, so let's see what we get. We get m equals, now if you, again, plug into this guy right here, well, we get, of course, it's a fraction. We get 1 plus 0.1 squared minus 1 over 0.1. Oh, if we simplify a little bit, 1 plus 0.1 is 1.1 squared minus 1 over 0.1. All right, now it's time to use a calculator, I guess. Go over here, handy dandy TI calculator. Let's see, 1.1. Hope that's not the right button. 1.1 squared minus 1 divided by 0.1. We get 2.1. All right, great. So that is the slope of the line that passes through P, which is 1, 2, and Q, which is 1.1, f of 1.1. Now, what if we let delta x equals 0.01, like we're instructed? Well, let's see what the slope is there. M equals, again, going back over here to this definition up here in the top right-hand corner, we have 1 plus 0.01 squared minus 1 over delta x, which is 0.01. If we simplify that slightly, that's going to be 1.01 squared minus 1 over 0.01. Then we'll go back to our calculator. 1.0 squared minus 1 divided by 0.01. Oh, I did not. Right. Let's say that previous answer divided by 0.01. All right. Hey, looks like some sort of pattern emerging. 2.01. Okay. Let's do the next one. Let's let. Oh, you know what? Oh, there's a typo there. For delta x. Ooh, delta x and delta x. I will fix that before you guys see this. So let delta x equals 0.001. So let's see what the slope is of this new secant line is. Again, going back to this guy in the top right-hand corner, we get 1 plus 0.001 squared minus 1 over 0.001, which simplifies a little bit to 1.001 squared minus 1 over 0.001. Can you guess what that's going to be? You should be able to. I guess. Let me say. Two values, not much of a pattern. Once we get the third one, you should see the pattern then. Okay, so 1.001. Oh, I did that again. That is not a square. Let's just start at 1.001 squared minus 1, enter, divided by 0.001. 2.001. Now you should see the pattern. So what do you suspect is going to happen if I didn't ask for it here, but let's say let delta x equals 0.0001. What do you suppose the answer is going to be? Here, let's just go ahead and guess. Equals 2.0001. Let's see if that's true. M equals, see, that's 1 plus 0.0001 squared minus 1 over 0.0001 equals, well, that's going to be 1.123 zeros, then 1 squared minus 1 over 0.0001. Okay, let's just verify. I bet that's our answer. 1.0001 squared minus 1 divided by 0.0001. Hey, what do you know? There it is. Okay, so here's my question. Hypothesize as to the true value of the slope of that line. So we have this series of secant lines. We have a point C here and a point C plus delta x, comma f of c plus delta x. It's getting closer, 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 closer. So we have those. Here we have 4 different slopes of 4 different tangent lines, and as you get closer and closer, the slope of the secant line gets closer and closer to the true value of the slope of the tangent line. So hope you recognize this. We're taking a limit. We're letting delta x get closer and closer to 0. We're taking the limit as delta x goes to 0. So this is kind of like using a table of values to evaluate a limit like we did in the previous chapter. So what does the pattern here show us? Well, to me it says, hey, I bet that slope is 2. I bet the true slope is 2. So slope of tangent line equals 2. Maybe question mark? I don't know. I think so. I bet it is. We'll verify in just a minute. All right, let's see. Here is our big definition for this video. Okay, we have one big definition today, and this is it. So consider a function f and a point c, comma f of c, like we've been doing. The slope of f at that point is given by this limit. The limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x. Now, if you were halfway paying attention in the previous chapter, you will recognize this because we did limits that were of this form. I never mentioned the word derivative, but they were derivatives, and this is a derivative. Okay, the slope of a tangent line is called the derivative of f at x equals c. And here is some notation for you. We will use throughout the rest of the class. That is read f prime of c. F prime of c. That's the slope of some function f at the x value x equals c. Now, if you do this limit, it will give you the slope. It will yield the slope of f at x equals c. So let's use this definition and the example, the function from previous example, to see if our hypothesis was correct. I put a question mark here. Let's verify if we can erase that question mark or not. Is that slope of the tangent line 2? Let's evaluate this limit and we can figure out. So let's see what we can come up with here. So our function in the previous example was, here, let's jot that down. It was f of x was x squared plus 1. And we want to find the slope, the derivative at x equals 1. So we had the point 1, 2. So that, remember, was our value of c. And we don't really care right now, but I guess technically 2 is f of c. We don't really care about that, okay? C is what we need to do this definition. So the limit is listed here. So here, I'll write it out again. F prime of c is equal to the limit as delta x goes to 0 of, this is called the difference quotient, f of c plus delta x minus f of c over delta x. So now if we say plug in for f for our specific function and our specific value of c, we're going to have f prime of 1 equals the limit as delta x goes to 0 of, we're going to have f of 1 plus delta x minus f of 1 over delta x. I just plugged in our value of c. Now what we can do? Well, we know what f is equal to. It's x squared plus 1. So we can evaluate f at 1 plus delta x and at 1 and simplify the numerator. Let's see what happens here. By the way, that was our general strategy in the previous chapter. You had limits like this, and basically what I told you is, hey, just do your best to simplify. And that's basically all we're gonna do. Simplify, do a little factoring, a little dividing out common factors, and we'll be home free. So let's see, if we plug in, just like we did in the previous example, f of 1 plus delta x simply means plug in 1 plus delta x into your function. So we had x squared plus 1. That is f of x plus delta x. We substituted 1 plus delta x into the function. That is f of 1 plus delta x minus f of 1. So what do you get when you plug in a 1? Well, we've already done this, but it's 1 squared plus 1. Okay, over delta x equals the limit as delta x goes to 0. Okay, so this is what you started with in the last chapter. You had several examples like this, where you had an expression, a limit that looked basically like this. Okay, perhaps this number in the top right-hand corner was maybe a little more simplified, but maybe not, okay? And your goal was just to find the limit, even though you didn't know what a derivative was at this point. But now you know a derivative is slope. We're trying to find the slope at x equals 1 for the function x squared plus 1. So now all I'm going to do is clean up a little bit. Here, I'm gonna not do too much at one time. I could do more right now, but I'm going to leave that as 1 plus delta x squared. But what do I have? I have 1 minus 2. The 1 squared plus 1 is 2, so I have 1 minus 2, so I get minus 1 over delta x. Okay, now, obviously we cannot, I should have said this already, so here's our limit. Obviously you cannot take that limit via direct substitution. You know, we saw that, lots of examples last semester, last chapter. You know, you try to take direct substitution, but here if we try to use direct substitution, we substitute in 0 for delta x, but that causes division by 0. Actually, it causes a 0 on the numerator and a 0 on the denominator, which is no good. So that's why we have to figure out another way before we can use direct substitution. So here's the other way. Simplify as much as possible. So let's see. Let's see here, limit as delta x goes to 0. Now, by simplify, I'm going to expand this term. Now, here's where you gotta be careful. Let me see. I'll do it off in the margins somewhere. I don't think we'll need the space down here. 1 plus delta x squared is 1 plus delta x, 1 plus delta x. Now, I see this all of the time. Please don't make this mistake. Don't tell me that 1 plus delta x is 1 squared plus delta x squared. That is not true, in general at least. We have to distribute, FOIL if you like to use that term. So 1 times 1 is 1. 1 times delta x is delta x. Delta x times 1 is delta x. Delta x times delta x is delta x squared. Be careful with that. Delta x is a single quantity. So delta x squared is just delta x times delta x, but you need to be careful with how you notate that. Okay? So I guess we could say this is 1 plus 2 delta x plus delta x squared. Okay, now come back over and substitute. So we have 1 plus 2 delta x plus delta x quantity squared minus 1 over delta x equals the limit as delta x goes to 0. Notice, add 1 and negative 1, you get 0. So we get 2 delta x plus delta x squared over delta x. Okay, we're getting there. We're getting close. Equals the limit as delta x goes to 0. Now, don't just start crossing out delta x's. A lot of folks get happy to say, yeah, let's just cancel all these things out. You might get in trouble doing that. Let's factor the numerator. So notice that both terms in the numerator have a delta x. So let's factor out a delta x. So delta x, if we factor it out, leaves us with 2 plus delta x in parentheses. And notice that's what we needed, because now cancel out, divide out, which leaves us with this. We divided out that delta x on the numerator and denominator, so we don't any longer have a quotient. We simply have a nice algebraic expression. And notice that delta x on the denominator was causing us problems all along. If we tried to use direct substitution, it caused us 0 on the denominator. Now with that gone, we can use direct substitution, because plugging in a delta x for 0 just results in, notice I'm dropping my limit notation because I'm actually taking the limit now. 2 plus 0 is 2, which is precisely what we predicted it to be with the previous example. Okay, so that is how we find the derivative of a function at a specific point. That's the process. Now, of course, it does get harder. That was a parabola, a quadratic function. We are going to have to deal with all kinds of crazy functions, but we're going to have developed quite an extensive toolbox to deal with this. But there's the process. It's called the limit definition of the derivative. We use the limit to find a derivative. We will have other techniques later. This is called the limit definition of the derivative. Okay, I hope you found this informative. We will hop on to the next video in just a bit. We'll explore a different way to think about derivatives. All right, catch you then.